Good morning, everybody. In today's class, we are going to discuss about the slope deflection method of structural analysis. So, let me give the brief overview about the slope deflection method. Slope deflection method. The slope deflection method comes under the stiffness or displacement or the equilibrium set of methods of structural analysis. This method is suitable when the degree of kinematic indeterminacy is less than the degree of static indeterminacy. Further, in this method, the joint displacement, that is joint displacement theta and delta, are taken as basic unknowns. In order to find the theta and delta, joint equilibrium equations are written. Joint equilibrium equations are written to find theta and delta. In case of frames, these instead of joint equilibrium equations, shear equations are written. Shear equations are written in order to find the theta and delta. Finally, in order to find the moments, that is the ultimate aim of the slope deflection method, to find the forces, for each span, force displacement equations are written. Displacement equations are written. And these force displacement equations are also called as the slope deflection equations. Deflection equations. Now I am going to quickly derive the slope deflection equation. So for that, I am going to consider a continuous beam. Derivation of slope deflection equation. So I am going to consider a continuous beam having fixed end at the extreme ends. There are two joints, A and B, intermediate joints, and there is a point load which is acting at the over the span AB. Let this point load be P. So the distance from the joint A to the load to the point where the load is acting is A, and from the joint B to the point where the load is acting is small b. Let the length of the span AB be capital L. Okay. So before deriving the slope deflection equation, I am going to give you the sign convention which is followed throughout the structural analysis slope deflection method. So sign convention So normally we consider the clockwise moments as positive and anti-clockwise moments as negative. In case of slope, the clockwise nature of the slope is treated as positive and anti-clockwise nature is treated as negative. In case of the settlement delta, in case of the settlement delta, which is obvious in the beam. So if this settlement produces, if this delta produces clockwise rotation, to the member, then delta itself is considered positive and it will induce anti-clockwise moment at the supports. I am writing you this very briefly since this point will be well observed only through a written statement, that is negative. Anti-clockwise moments, that is the negative moment it will produce. So using these sign convention and taking the continuous beam, we are going to derive the slope deflection equation. So for that we are going to discuss about 4 steps. So initially I am going to give the step 1 involved. So as I have given the loading in the span AB, which is acted by a point load P, however it is not acting at the midspan, it is at a distance small a from the joint B and it is some other distance B from the joint B. So due to this loading effect, there would be end moments which is developed at the joint A and joint B. So the fixed end moment, which I have denoted as m bar f AB, will be equal to minus PA square PAB square upon L square, where capital L is the span, length of the span AB, and similarly the fixed end moment that is developed at the joint B, that is m bar f BA, will be equal to PA squared B upon L square. This is positive and this is negative. So overall, in general, these are the moments, fixed end moments, which are developed at the joint A and B due to the loading effect on the span AB. So next step, I am going to give you the moments which are developed due to the rotation. So since the span AB is acted upon by the load P, it is obvious that there is rotation, there will be rotation in the at the joint A and at joint B. So due to this rotation, there would be moments which are being developed at the joint A and B. So due to loading in span AB, if theta A, let theta A be the, if theta A be the rotation at ND at joint A, then the moment developed at the joint A will be 4 EI upon L theta A. So from the basics of the structural analysis, we know that if a particular moment is developed at a joint, at the opposite joint or the same span, some other moment, carryover moment will be generated. So this in turn will give rise to carryover moment, carryover moment at joint B. The carryover moment will be 2 EI upon L multiplied by theta A. So this is the moment that is developed due to the rotation at the joint A, and due to this developed moment there will be a carryover effect, and because of this carryover effect, carryover moment will be developed at joint A, and the carryover moment will be equal to 2 EI upon L theta A. So similarly, I am going forward to the step 3, wherein I will be giving you the moments which are developed due to the rotation at joint B. So in the step 2 we have seen the due to the effect of loading there is a rotation at the joint B, and due to that moments are being developed and are at both the joints. So similarly, due to the loading effect in the span AB, there will be rotation at the joint B. Let that rotation be theta B, and because of this rotation there is a moment which is being developed at joint B, which will be equal to 4 EI upon L multiplied by theta B, and due to this developed moment at joint B, there will be carryover moment developed or induced at joint A. The magnitude will be, this is at B, joint B, and this is at A, 2 EI upon L multiplied by theta B. So this step 3 is more similar to the step 2. However, we are considering the two opposite joints in the same span. Now I am going forward to the step 4. If delta is the relative settlement between joint A and B of span AB, between joint A and B of span AB, then the moment which is developed at end A will be equal to, due to this relative settlement, moment that is developed at end A will be equal to minus 6 EI delta upon L square, and at B will be equal to minus 6 EI delta upon L square. So this negative means moments are produced when delta produces clockwise rotation to the member. So this comes as a follow-up of my sign convention which I have already given. So next we will give the final slope deflection equation. So for that, whatever the moment we have developed, or whatever we have derived over the 4 steps, we have to sum it up, and then we will be getting the final moments at the joint A and B. So initially I will give the final moment at the joint A, So the final moment, the notation I am using is M bar AB. So this I will get as a summation of all the moments that is developed at joint A from the four steps, following the four steps. So MF bar AB plus this comes from the step 1, 4 EI upon L theta A. This comes from the step 2 plus 2 EI upon L theta B. This comes from the step 3 minus 6 EI delta upon L square. This comes from the step 4. If you sum it up, or if you simplify further, we will get M bar FAB plus I am taking 2 EI upon L as common. So within bracket I would be having the quantity 2 theta A plus theta B minus 3 delta upon L square. So this divided by 3 minus 3 delta upon L. So this is called, this equation is the final slope deflection equation, or the equation is also called as the force displacement relationship. So this is the equation which is required to find the final moment at joint A. Similarly, if you sum it up all the moments which we obtain in all the four steps at the joint B, we will be getting the slope deflection equation at the joint B. So let me write the equation at joint B also. Final end moment at B. This is, I use the notation M bar BA, which is equal to M bar F, that is from the step 1, plus 4 EI upon L theta B, this is from the step 2, plus 2 EI upon L theta A minus 6 EI upon L square multiplied by delta. If you simplify this equation further, you will get M bar BA, which is equal to M bar F BA plus 2 EI upon L. I am taking it common. You will get 2 theta B plus theta A minus 3 delta upon L. So this will be the slope deflection equation for finding the final end moment, at joint B. So in the next class we will see how to solve the numerical for the given continuous beam using the slope deflection equation. Thank you all and best wishes.